It's such a pleasure to be back here. It's been 21 years since I started just across the road before this was a lecture room. And it's a very fine conversion. I think it's a great use for this. This is what I learned neural networks. I was doing sort of that as an undergrad project, and there was someone that got me into it. And this place in particular is the home of many of some of the greatest researchers that kind of led to what we're doing here. People like Seymour Papert at MIT, he started here. I mean, even a lot of the computing that you're using, I mean, you obviously probably know about EC2 and so on, so a lot of things have come out of this place, and we ought to be proud of that. At the same time, and you probably noticed, can you hear me well at the back, actually? Yeah? Okay. Yeah, I have a bit of a cold. I had to go to a conference in Copenhagen, fly back, just had a few hours, take another plane, fly here, finishing slides. And at this conference in Copenhagen, a conference called the EMNLP, it's a large language conference. The organizers were, at the beginning, saying where the different publications, the different submissions had come from in the world. There was lots of submissions from the US, as you'd expect, some from Europe, Canada, and so on. And sadly, there were, take a guess, how many from Africa do you think? That's right, he guessed it right there. There was 0. And you go to NIPS, which is a machine learning conference that happens in December, and there's about 6,000 people. Take a guess how many people, I actually don't know how many people from Africa attend NIPS, but it's a very small amount. I remember 10 years ago, I was sitting in the audience at NIPS, and the organizers went over where the papers had come from, the submissions. Never mind being accepted, just sending a paper, just making the effort of sending a paper to one of these conferences. And they also pointed out in those days that from Africa we had nothing, and they even made a joke out of that, which was upsetting for me in the audience, and for there was one other person from Africa there. The climate is very different now. People are very respectful and aware of the fact that there is a lack of participation. But that lack is certainly not mirrored by what I've started with, saying that so much has come out of here. I think it's time to, build more capacity in Africa. I'm stating this because you were selected from a large group of people. Whether you're a student or a professor or you work for a company, the fact is you're the best hope that we have. So I'm really glad that you made this effort to be here, and I'm really grateful for the effort that you will all make for the next 10 to 20 years, changing how this continent participates. There is a big dialogue right now in the world about the future of artificial intelligence. We're building software systems that will control most of the world, that will control our economies, that will control our healthcare, that will essentially control our future. If we don't participate in that, we will be left out. We will not be able to get equality. And that is like a huge problem. We need to be able to level the ground. And Africa has so much to offer. I mean, this is the home of Nelson Mandela. And it would be wonderful if it would be so sad that a nation that has produced so many great ideals, does not contribute toward that world climate. I know some of what this is coming down to is, I know some of these tutorials might be hard. For some of you, it'll be easy. For some of you, they will be hard. I was looking at the paperwork. For me, it was hard. It was like looking at all these exercises and the tutorials. And I was like, oh my God, these guys are covering so much. And, but I thank you for making the effort. And I'm going to be here for the week. The organizers are here for the week. Shakir and Ulrich and everyone, they've done such a wonderful job, devoting their time to this. So please take advantage of us being here, and we'll try to make the most out of it. Gentleman over there. So this is a question of ethics. So that, I don't know if there's a topic or there's a session on ethics of AI. There isn't one? Maybe if we have time on Friday, we should have one. Okay, we'll try to organize a session to address your question. I cannot address your question in 2 minutes. This is an important question. But let me just proceed by saying, currently, about 1.2 million people die every year in the world because of car accidents. It's one of the biggest killers. And self-driving cars could address that. But of course, we need to be thoughtful as to how we do it. There's all sorts of legal issues that many folks are thinking about. Ethics and so on in AI is in itself a field of study now that, like if you're interested in that sort of thing, I strongly recommend you join that. Anyway, my talk today will be, let's take a few steps back and go to the basics. And I'm going to go over convolutional neural networks. A lot of the slides that I'm covering today were produced by Martin Gorner. He has a very nice course that I recommend to everyone here. It's called TensorFlow without a PhD. Deep learning in TensorFlow without a PhD. And it's beautiful. It has slides, exercises, and so on. You go to the web, you can get everything. And then Karen Monian, one of my colleagues at DeepMind, and also I think one of the best researchers in convolutional networks in the world, certainly one of the ones that has won the ImageNet Prize and has made some profound contributions to ConvNets, provided most of the other slides, and they're slides that DeepMind uses for teaching a course at the University College of London. Okay, so I'm going to cover the following. I'm going to go first through a recap of what happened yesterday, and let's just make sure that we sort of solidify some of the knowledge. I was told you were doing a lot. Then I'm going to go into what is a convolutional layer, how you put convolutional layers together. And in fact, you should start thinking of, when I say layer or module, think of it as a Lego piece, because that's what deep learning is like, putting Lego pieces together. And if you learn to reuse the Lego pieces, you can make lots of cool things. Then I'm going to talk about how you build the state-of-the-art networks that we use today. And finally, go over some applications. For most of my lecture, I will use images, an image classification, because it's sort of, for no reason that it's visual. You can see the image, you can see what's going on. But this applies to any type of signal, whether it's images, whether it's video, whether it's text, whether it's a time series, et cetera, et cetera. So you could use this for all sorts of things. Okay, so recap. TensorFlow and deep learning. Like I said, this course, TensorFlow and deep learning without a PhD, highly recommended. All right, so I think you had trouble downloading MNIST yesterday. Is that being sorted out? Or probably folks are working on it right now. So MNIST is just a data set of digits. It's considered a trivial data set by today's standards, and pretty much solved. It was very important at one stage when Jan LeCun started working on it, because in those days, when you worked in the post office, you basically would get a letter. There were folks who would, their job was to get a letter, read the address, and then based on the address, put it on a particular tube. And this is what they did for 10 hours. And then this network allowed us to sort of automate that kind of tedious job. Now, yesterday you probably saw that sort of the basics of how you build a one-layer classifier. So if you have an image that is 28 by 28, 28 times 28 gives you 784. So when an image is grayscale, like of a digit, that's represented by 784 numbers. So we flatten the image, and then the task is, for each image, we try to predict whether the image is a 0 or 1, and so on, up to a 9. So you're just trying to predict which digits are in this post office code. And you were introduced to logits. So what logits is, you make these predictions, call them ln. We're going to go over what ln is in the next slide. And then we feed them through the softmax function. What the softmax function does, it just basically converts, it just divides by the sum of all the e to the ln's, so to make sure that everything sums to 1. So you get a probabilistic interpretation out of this. And essentially, what you do is you take all the images. Each image, as shown here, will be a column in the matrix. Actually, I don't know if I can point, because if I point, it will not get recorded. Oh, let me get, I have an idea. Oh, brilliant. Okay, that's my point. So that will be recorded. So you have this image here. So this will be all the 8s, and each of these columns will be an image. And you also have a matrix of parameters, because what you're going to do is you're going to multiply every pixel times one parameter. All these parameters are these unknown knobs that we're going to have to tune to figure out the best way of predicting the right number. This L that we had in the previous slide, that ends up then being W multiplied with one of the x's, and you're going to do this for each of the images. That gives you the predictions for the 10 classes, and then we also add these parameters that are the biases. So this is basically the equation of a line, okay? Like you probably saw it as y equal mx plus b. So x is the input, y is the output. W is just a slope. In this case, it's no longer a line, but it's a plane, a hyperplane in high dimensions. And b is what allows you to lift it. So all we're trying to get is all the possible degrees of freedom. So we can move it like this, and then we can shift it up and down. So we can represent a wide class of decision boundaries to separate the numbers. And so we do this for all of them. And so that's basically it. That's the model. That's the neural network. It's a single neuron that takes several inputs, x, whoops. It takes several inputs, x, scales them, and then you add the bias. This, if you have 100 images, each of size 784 pixels, gets multiplied by this matrix of parameters that is very large. There's 7,840 parameters. And then you add these biases, 10, one for each class. And we can add this like this, and it works because of the properties of Python, so you broadcast. Writing this, so one of the nice things about machine learning is you'll find if you write an equation like this, writing it in code is pretty much the same thing, especially if you use one of these packages that we have these days, like TensorFlow, or PyTorch, or DyNet, or MXNet. So these are very nice so I think one of the revolutions that's happened in deep learning is that folks have created these packages that have all the software. And here I'm going to show my age. When I was a PhD student, the first thing I did when I got to Cambridge was code a matrix library. And then that was the start. There wasn't such a thing as great matrix library. And then you had to do everything by hand, backpropagation by hand. Then I had to do RNNs, and I had to figure out backpropagation through time. And I tried it, and eventually I gave up, and I invented my own way of doing it. I invented a different algorithm just because I couldn't implement the other one, because it was too complex. There were only 2 papers at the time you could use to implement it. There weren't resources, there weren't blogs, there wasn't anything that could help me get that. It took a long time before I could get that idea and be able to code it. I think I still have not coded that. I still haven't gone through that exercise. But nowadays we have these software frameworks where pretty much everything's been coded. And each module in the software framework, again, see it as a Lego piece. And you can put the Lego pieces together and compose things. And once you finish composing that, you can take that model and you can put it back on the cloud for someone else to use. And then you keep building. And because of that versatility, we've seen this explosion of applications. Because the software is out there. And you can use that. That software is available to all of you. You can have access to it and play with it. So in this case, we're using TensorFlow. You also learned about the cross entropy. So the cross entropy is a way of checking how many mistakes is the model making. And so basically, the more mistakes, so the process of learning, as we're doing it here through optimization, it's essentially a process of trying to define an error function. Think of it as like a bunch of mountains, like the Drakensberg. And then you start somewhere in the Drakensberg. You look for what is the steepest direction, and then you go down carefully. You have to, I guess, adjust your learning rate going down. And so entropy makes sense because the entropy is a way of measuring uncertainty. So we try to minimize the uncertainty. We try to become more certain about the label predictions. If you have a coin, if the coin is unbiased, 50-50, that's the highest uncertainty it has. So you can actually do it with the coin. If the coin becomes biased, then there's less uncertainty because if it's got lead on one side, you can easily predict which side it's going to fall. There's many other measures of uncertainty. There's Gauss-Hattie came up with L2 and so on. Now, what we're trying to do, again, is we're trying to predict the actual labels, which is done as what we call a one-hot encoding. And this basically says that the correct label for this image is a 6. And so when you make a prediction with the softmax, this is what the prediction will look like. So as I said, you try to do this so that it, I don't know why these don't add up to 1. These are the L's, I guess. And then you compare the 2 vectors. In TensorFlow, it's really easy to implement a linear classifier. Yesterday, you went through the painful exercise of doing it all by hand, kind of getting the gradients by hand and so on. And it's important to do that because you get a good understanding of it and how the packages work. And you can just use the package, but if you actually want to create your own modules, it's important to know about gradients and so on. So in TensorFlow, one of the first things we do is we import it, we create a place. So we're building this computational graph, and the nodes is essentially operations that we're going to perform on the data. And so we also have to create, basically when we create the graph, we have to sort of tell the graph, what's this going to be? What's this edge? What's going to go in this edge? What are these different, what's the structure of the graph? And the reason why we pre-generate that is so that we can then take advantage of automatic differentiation. So we can compile it to a format that allows us to get derivatives automatically. And that can happen on a computer. It can happen on a cell phone. It can happen on any hardware. So the advantage of doing this is, of course, to have that versatility of being able to run your code on the same code will run on any device. And then we create, eventually once you're done, then you run this thing. You will run a session that executes the operations. There's different ways of doing this. I'm going to use TensorFlow for this lecture. So if you're interested, there's also this package called Torch, which is also very good. I have some lectures in YouTube. There's a deep learning course. I did that in Torch, and there I explain a slightly different philosophy in the design of the code. So we create a place where we're going to put the data. In this case here, for the images. So there will be 28 by 28, 28 pixels by 28 pixels. There will be grayscale, so there's only one channel. If they're RGB, there'll be 3 channels, red, green, blue. And TensorFlow allows us to sort of use this non-variable to allow us to specify something later. Like in this case, that will be the batch size. And then we have the weight matrix and the biases, and then we initialize. The whole model can be implemented just with one line, which is this thing here. So we first make sure that X and W have the same shape, the same sizes, using reshape. These things, basically, I never remember the syntax, although with time as you're programming, you become better, but you can just Google, and that will bring you the function, and then you can check exactly what arguments this thing takes. You multiply them, add them, put them through the softmax. And then, of course, you also need the data, the prediction, the actual true labels. And then we compute the entropy, which is just the true labels times the log of the predictions, which were obtained with this module. That gives us the cross entropy. Reduced sum is just summing over the data of the batch. And we can also have functions that, for example, check whether the predicted label is the same as the true label. Okay? And we can keep track of the accuracy of our model. We then need to specify an optimizer, and specifying which optimizer. So you always have these two things. You need to specify a model, which we did in the previous slide, and now you need to specify what are the operations going to apply to the parameters of the model using the data. And in this case, what we're going to do is we're going to do gradient descent. So again, if you go to the Drakensberg, first you specify the landscape, and the second step is you specify how you're going to go down that landscape to get to the lowest error. The higher you go up, the more error, and then you go down. So if you follow the steepest descent, that's what this thing will do now, the gradient descent. But you could also do it you could try to sort of come up with other methods. If you did random sampling, that would work okay in 2D, but it would not work well at high dimensions. But folks do source different combinations of these methods. We'll just use gradient descent. That's one of the most effective ways of doing things. And then we specify an operation of what we want to do. What we want to do is we want to use this optimizer to minimize the cross entropy. Actually, I'm going to skip. The whole code is this. Okay, so if you want to build, this includes everything. So this is what we just went over to get the data, to reshape it, and so on. Get the loss function, get the optimizer, and then we create a session. We initialize everything, and then we're going to iterate this algorithm for a few steps. 10,000 here. There's a lot of code for loading data. So like to load the MNIST, this problem has been solved for you. It's not like you need to write code that will go get the pages of code as to how to do this. If you get your own data, you do have to write a function that will load the data and so on. And these are data loaders, but you can check how people did it for this other data set. You can modify that code and write your own data loader. But right now already we have some really nice data loaders that will take a small batch of data, like in this case 100, and then this is just done so that so we create a dictionary in Python. I think most of you hopefully have done. Who's familiar with a dictionary in Python? Okay, most of you. Good. So you've been paying attention to your tutorials. And then this session.run is just basically just applies an operation. So you compute. So you take that data, and for that data, you run a training step. And then you can compute the accuracy, and so on. And every time you do something, you run a session. So the way of programming here is not like Python or MATLAB, where you basically say what to do, and it will print this, and it prints this. But rather, you need to sort of create a whole structure of your program. And then to run like any operation, you have to sort of apply. You have to do that in a session. Simplicity and so on, and that for this case, this thing works fine. Stefan, are you around? Are you going to cover that? Yeah. Yeah, there's a lot of other considerations, and even like how you save your parameters, how you save your results. Of course, the larger your system becomes, the more you need to start thinking of what database structure you're going to use, whether you're going to serialize, whether you're going to store in batches. As the parameters get very large, and we're talking really large here, we need to also start thinking about how we're going to distribute them and so on. I will not sort of go into the scaling issues, because I think you can actually do a lot without going there. But of course, in the privacy of your own room with your laptop, you can sort of implement all these things. This is sort of a start, but there's a lot more. But what I really wanted to highlight here is that if you have one of these frameworks, this is it. This is everything. Implementing a classifier for images is really trivial. It's that amount of code. Provided that you spend some time learning what all these lines are and you play with it, this is pretty much it. Or you can also go the various other ways that you've been taught how to do it in the tutorials. Of course, we want to go deeper, and I'll soon go over why we want to go deeper. By going deeper, so we had one neuron. Now, a brain with a single neuron is not very interesting. We would like to add more neurons to be able to represent more complex data. And in particular, if you think of each neuron as representing a simple function, it's like a little brick. If you now have lots of them, you can compose very complex functions. So a brick is not very interesting. But if you have trillions of bricks, you can build Johannesburg, right? Many other cities. So we're going to try to come up with a classifier that does this. And then each of these nodes will apply a linear mapping, and then it will go through a sigmoid function. So we're going to introduce these nonlinearities. The sigmoid is basically comes in from, it has different motivations. So in neuroscience, Jeff Hinton once told me he was he wanted to implement something that was off and then would be on. And so off and on was not differentiable, so he came up with a smooth way of being able to differentiate through that gate. But this also has a history in, in psychology, and you can even sort of prove some theorems about this when you have trying to discriminate to Gaussians. Now that we have more layers, so we had 200 units, and then 100 units, 60 units, and then 30 units, and I often interchangeably call these things units and neurons. For each of these, we will have to create the variables for the weight and so on. And this is a lazy way where you do it one by one. And you can sort of make this code a bit more efficient, as explained in the tutorial. And then you also would compute all the transformations of every layer. So, and layers here also come from biological motivation. And I'll get into that, why we call these things layers in a bit. Sorry, go ahead. Mm-hmm. You're ahead of me. Maybe I'm going too slow over my recap. I'm going to come to those 2 points. If you bear with me for a few seconds. So I was just trying to do a recap for whoever was feeling a bit lost yesterday. But I'll try to get to those 2 points about vanishing and having too many layers. So when you do this for MNIST, you can plot your accuracy or the how well you're doing, how many examples are you getting right, or you can plot the loss. And this particular classifier is actually not very good. Okay, so it's getting an accuracy of about 80%, a bit less than 80%, and that's not considered very good for this data set. You want to be on the very high 90s for this. And as the gentleman just pointed out, you can do ReLUs. ReLUs also have a long history. There was a very nice recent paper. There's also by Nair and Hinton discussing them. But you actually can sort of find them in other papers in the literature. And in fact, they go back to Fukushima's early work on something called the new cognitor, which was one of the earliest ConvNets. And if you do that, things improve a lot, as he anticipated. But there can still be problems, even when using ReLUs. And this is probably the most important plot I can show you today, which is, did you cover cross-validation yesterday? Okay, so one of the most important things in machine learning is cross-validation. You never train on the whole data. You split the data, typically into 3, or you could even do more. Usually the 3 partitions is you use one partition of the data for training, and you use another partition to sort of estimate hyperparameters. And then the third partition, you never touch. That one you only touch when you're done, and you think, I finished, then you check. Okay. And that's what's going to give you sanity, like make sure that you're on the right track. Because if you check and you don't have good results, that means you probably have an issue. You have the wrong model, or your model's not big enough, or you don't have enough data, or you need to sort of go back and do some thinking about what model you should use. And it's important to do well in each of the partitions. Doing well in one partition and not well in another one is not a good idea. Because if you go to your boss and you're like, look, I have this amazing ConvNet. It completely predicts whether there's a pedestrian in front of the car. It works beautifully, 100% accuracy. And then you trial and you end up, it doesn't detect the pedestrians. That could be problematic, right? So we always are trying to find what's the worst error. And so in this example where because we have the cross entropy, we can plot the cross entropy for the training data and the cross entropy for the test data for this data that we don't use for training. And usually some folks try to stop here, because what happens on your training, you're getting better and better and better, more confident, but then on the other data set, your error starts going up. This is what we call overfitting, and it's the thing to watch out for. One way to prevent overfitting is dropout. I have no idea why he picked these pictures. But you can actually watch his video online, which I haven't watched. So the idea of dropout, that's a smart idea of Jeff Hinton. So what he did was, like if you take, during training, you apply a mask to some of the units. You remove some of the units. And why is this? I told you these units are like bricks, and you put bricks together to build mansions. Now sometimes so these bricks can be negative. They can be the anti-image. They can be like antimatter. And so what happens is because there's some are positive, some are negative. So you put one brick, and then you put another brick that blanks the other brick. So you need to put another brick because the other one is blanking. So the units sort of codepend on each other. And by randomizing this dependence, they can no longer do this. Because if you remove one of the bricks, then the other one, you can't add an extra one to compensate, so that one has to be removed. So the idea of this dropout is then to prevent that one unit learns to make use of the other units as opposed to doing something useful. And again, in TensorFlow, this implementing the relo as opposed to the sigmoid and then doing a dropout is sort of very trivial. It's 2 lines of code. Like I mentioned, deep learning is like playing with Lego, but not like this. It's more like this. These days, there's a lot of Lego to play with. And this is kind of the game, as was pointed out, is how to make these Lego things deeper. Because when they become really deep, we get better results. And of course, not everything is just straightforward input to output, but also we create all sorts of structures. Like you're going to learn about recurrent networks, and tomorrow about variational encoders and so on. And we really start building very complex models that don't necessarily have this sort of input to output line, but they can have a memory that they can go to the memory, get stuff, they can process all sorts of things. So the structures can vary. It's no longer sort of just a sequence of modules, but they can be arbitrary graphs. Now, let's get into convolutions. A lot of images have the following properties. Sorry. Okay. Because people cheat. So here's what could happen. The third one is the one that keeps you honest. Because what happens is that sometimes you train and then you test. And you're like, oh, I'm not getting good performance. So maybe I'm going to change my model a bit and train again and test. I could get a bit better by fine-tuning this. And then if you keep doing this over and over, you start doing well both on train and test. But what you're doing really is you're overfitting on this combined data set because you keep looking at it. And the moment you're looking at the test, you're training with the test. So you're no longer being honest that that's really test. And so this other one is when your job is finished, when you're done, you have your detector for detecting people in front of cars. And then at that point, you give this to someone else, your model. And it's even better if you never see that data. That third data set, you should not have, that should be a different department in the organization that takes your model, checks it, and then gets back to you and tells you, Nando, that model would have killed all the pedestrians. And or like, yes, it works. And I think we now can automate this. Yeah. So eventually you do. You could overfit to a third data set. But the hope is that you don't do that. The hope is that you don't, that there's enough randomization, there's enough data that that third data set could even be changing. Someone could be playing adversarially with you. Cross-validation works when there's lots of data. And a lot of the things we use neural networks for are things where there's a lot of data. But if you have very few data, you need to be very careful with how you do it. There's more advanced techniques. So one that's very nice is called the bootstrap. That is about randomizing, sampling data sets at random from the data. And this is sort of, in itself, a big topic of study in statistics. In machine learning, we sort of become complacent, especially with MNIST. I mean, if you think about it, MNIST has a test data set. How many times do you think people have used that test data set to prove that the paper that they're publishing gets better accuracy? So it's being used to death, to the point that it's no longer a good. It's just a data set that's good enough to make sure that you're on the right track, but don't use it to as a means of thinking that you have the best model in the world. Yeah, thank you. That's a very good point. So so when you split, so he's asking what happens, because you're splitting the data sets could have different properties, and there's this question of independence. So in statistics, we want the data, in fact, we want this data to be independent for this to work well. There might be some relaxations that you could study with Bootstrap and so on. But so what we're assuming is that this data has the same properties, the trained data and the test data. If it came from a different distribution, then it wouldn't make sense to transfer from one situation to the other. Although, in some cases, people come up with spatial techniques to be able to do this kind of transfer, to be able to deal with data sets that sort of have slightly different properties. So that's, for example, when we do imitation in robotics, where I will collect, so the folks that I work with in my team, they will collect data, for example, for a human person doing this. And they collect the video and they train models on that, control policies, or how to go from observations to the right action. And then we try to transfer that to a robot arm to do that in the factory. And so then the two data, so we transfer from one data set that has some properties to a data set that has different properties, because the robot arm usually looks different than, even if you look from one human to another one, there's a change. And also, you'll see it later today when you go into recurrent neural networks, that this assumption of independence sort of goes away. The data has some particular structure. So what I do today sort of depends on what I did yesterday and so on. I'm going to take one there and then. Sorry, could you repeat? I didn't follow you. I'm going to take your question during the break, because if you've modeled the error signal, so in a way when you're modeling the data, we're actually doing both things jointly. I'm going to go over that later with you, I think. So you should have some control as to how you partition the data. And then you need to be able to justify, like the gentleman pointed out here, questions of that the data is independent and so on. So as you're constructing a data set, is not done like this. In fact, it's the most interesting part. I mean, TensorFlow models and so on, you do this course and you know all the stuff. This is easy. We know the answers to all this. But coming up with a new data set, that's where the opportunities are, because then all of a sudden you can do a new thing. You can do a new prediction that no one thought about, which if I get through my slides, I will get to a bunch of examples. And of course, you do have to think carefully about how you do it. And folks do try. And there's ways in which you could construct a data set that would be biased in one way or the other. So you always ought to have that in mind. All right, so one of the problems with the previous classifier is that we've been building up. Go ahead. Yeah, so one simple way, you should at least break it into two, like for your own sanity. I suggest you break into three that are about the same size. That's a good way to do it. And then beyond that, there's this book called The Elements of Statistical Learning. Elements. It's online and you can download it. So this is by 3 professors at Stanford. One of them South African, Hasti. And they cover like all sorts of ways of doing cross-validation, all sorts of ways of doing bootstrap. There are many books written on this topic. This topic alone as to how you break the data set is being widely researched for many years. All right, folks. We were meant to have a break, but I have not even started with doing ConvNet. This is the first slide. Do you still need a break? Okay, since we've gone slow, feel free to go and comment. ConvNet, and I'm going to accelerate now. And so if you have questions, I urge you to please wait for the break, and I will be here for the next week, and you can ask me during that. I'll have my laptop with the slides. There's 2 special things about images in particular, and a lot of data. One is locality. Like important events might be just located in a particular region. The same as if you're doing fMR, if you're looking at time signals with speech, the voice might have happened at a particular point in time. So there's that locality, and also invariance, like whether the hand is here, or whether the hand is here or here, you still recognize it as a hand. And so we would like to build models that take advantage of this, more efficient models than that huge neural network with lots of parameters. So one way to go about this is instead of using the model that we had before, which is this, which basically you have one parameter for each part of the image, we try to build local models so that only look at particular points in the image. So this is based on this idea of a receptive field, and humans are also masters at doing this. When you Actually, our vision is slightly different. It's actually sequential, but you actually only see at a high resolution something that's of the size of your thumb when you put it at this thing. And you see 3 of these every second. And you have a blind spot, so there's a big black spot here that you don't see. And in fact, you don't see any of this, any of what you're looking at. It's mostly, it's an illusion constructed by your brain. Which can be fooled. Like, I have a lot of illusions that can show that. I can do that some other time, if you want. And so we want to sort of have this locality. And now what we're going to do here is we have this neuron that looks at a particular region of the space, and it generates an output. So the output of looking at all of this input then results in itself in an image. We're going to do one thing better, and it's that instead of using instead of using different units for different parts of the image, what we're going to do is we're going to use a single unit, a single neuron, and what we're going to do is we're going to scan that neuron over the image. So this is no longer sort of biologically possible, but however, the idea that you have a unit that you scan for something in the world is very much how the visual cortex seems to work. Now, what is this? And this is basically convolution. So what is convolution? Suppose your image has 3 pixels. So in this case, my pixels are x1, x2, and x3. Just 3 numbers. So this image is not 2D, it's a 1D image. So I was thinking of how to put together like the simplest example of convolution. So you start with this image that has 3 pixels, so the size of this image, and you're trying to produce an image Z that has, you will produce an image Z that has 2 pixels. The idea of convolution is sort of illustrated by this. You multiply W1 times X1 and W2 times X2 to produce Z1. So it's this equation. And then you slide the filter. We call these things filters. The weight matrix, in this case a filter. We slide it like this. And then we compute W1 times X2 and plus W2 times X3, and that gives us Z2. So, and that's basically the basic convolution operation. So you just take a filter and you slide it over the image. And every time you slide it, you multiply the filter times the image. Now, this is essentially, for those of you who've done this in engineering or in statistics, this is called a correlation, so it's the dot product. If you have 2 vectors like 1, 0, and 1, 0 in your dot product, you get a big answer. You get an output 1. But if you take 1, 0, and 0, 1, and you dot product them, multiply them, then you get 0. So they're anti-correlated. So in other words, the closer W is to the input, the higher the value of Z. So if W, and W itself is an image. So if W is an image of a cat, and you move that image over the world, you're essentially looking for a cat. If it's an image of Shakir, I start moving it, and it goes like, and it gets Shakir because it finds an image that matches. That's how your brain works, by the way. And of course, why do we call this convolution? Because it looks just like correlation. You can flip the filter, and this flip operators, you just change the order of the filter. And then if you flip, you can rewrite this equation in this form. So this equation here is just basically a way of summarizing both of these 2 equations. I recommend you go over this in your own free time, that you check that the math here is correct. And then if you flip, you can rewrite it like this. And this is the convolution operator that you learn if you're here at WITS in the building next door. I remember learning it in 2nd year here. For images, now the filter is itself an image. So in this case, I'm going to consider this particular filter here. And imagine that it's 0, 0, 0, and when there's the red dots, think of it as 1s and 0. And here is the input image, so it has this shape. And let's say that the value of the pixel here is 1, 1, and it's 0 elsewhere. So when you multiply the filter times the image here, you get a 0, okay? Because at that position, there's no, the reds and the grays don't overlap. So you basically have 1 times 0, 1 times 0, and because everywhere else where the filter isn't, you don't multiply. So it's 0, 0, 0, 0, 0, 1 times 0, 1 times 0, 0 times 0 gives you 0. You can move the filter, and in this case you have 1 times 1, 1 times 1, 1 times 1, 0 times 1. So if you add all of them, you get 3. In this case, you get a 0, and so on. So you're basically moving this over the entire image, and I'm just showing it here over a few positions. And once you do this for every possible section in the image, the output image that you get, we call this the feature maps. This feature map will have these values that we computed by going one by one. And it will look, if you plot it now as an image where 3 is darker, 2 is a bit lighter, and so on, it will look like this. And what this is showing you is the darker it is, it says the more likely it is that you will encounter this L shape. So it's basically saying there's an L shape here, there's another L shape here, that's why both of these are dark. Here it's almost an L shape, it's missing this bit here, but it's almost an L. So it's a bit darker. And then where there's 1 pixel and so on. So what it's doing is exactly that. It has this L shape, and it's moving this L shape over the image until it finds it. We have face detectors in our brain, and we do the same thing. We detect faces. And it's something we do very early in life. In actual images, each of these images that I'm showing you here, one of these little images is one of the detectors. When you learn a convolutional network, and I'm showing here a convolutional network by Matt Zieler and Rob Fergus that had several layers and won a big competition that I'll get to later. The different filters that it learns, and essentially what we're going to do is we're going to learn one, so applying a single filter gives you an image, and what we do is we actually apply different filters. So one filter gives us this image, another filter gives us this image, another filter gives us this image, and so on. So, and when you train this, so this is basically how you construct the model. And then you train it by gradient descent, just like we did with a bit of code that we had before. You learn like that what these guys are looking for, they're looking for edges, or the further up you go to layer 2, layer 3, they start looking for different shapes. So as you go up, you even get things that look like this. You start seeing dog faces. These are neurons that will respond to a dog face if they see a dog. You can take models like this model, and you can map it. Actually, you can do experiments and map it to the visual cortex, and you find 19 neurons that will be doing the same responses. And again, just to emphasize, a single image here is a weight matrix. And it's like this guy, like the L. Except that you learn. Instead of assuming that you know it beforehand, you actually learn all these matrices. Now, here's an interesting experiment. I don't know if I'm online. Okay, I might not be online. I might not be able to play this video, but I can play for you later. This pretty much summarizes the history of ConvNet and how we got here to today. Hubel and Wiesel in the 50s did this experiment where they had a screen that had a sort of a beam of light, and there were some patterns on the wall, and they could move the grid of light to be over the patterns. And then they were taking measurements from the visual cortex of a cat. We also have it here at the back. And they were recording with very blunt instruments at the time. And then what they realized is when the line of light, for a particular neuron, if the light was sort of the same angle as this feature here, they could train the neuron to be good at detecting this inclined line. And so when the monkey sees the inclined, sorry, not the, in this case the cat, when the cat sees the inclined line, that neuron fires. But if you change the angle of the line, that neuron stops firing. So it's like that neuron is doing a specific line. And the reason why they can also test this is, and you learn them. You're not born with these necessarily. And they test this because they take a cat, a cute little kitten that only sees vertical lines, never sees horizontal lines. So it never develops the detectors for horizontal lines. You can actually look into the cortex and see that they're not there. That's the magic of the brain, at least vision, a third of your brain. And there's more to it, but that's approximation. So that's basically the operation of convolution. And so I'm now showing you here with an animation. I think it's by Vincent Dumoulin. And essentially, that's basically how it works. So here we have a filter that's 3 by 3. And that filter multiplies this image that's 4 by 4. And the output is an image that's 2 by 2. So the filter is also called a convolutional kernel, or the weight, or the weights. It's an image. And so here we're going from 4 by 4 to 2 by 2 by applying it like this. And there's many ways in which you could do this, and this is the magic of TensorFlow now, all the different ways. So we can do it the way I just described. You can also apply the filter to an image that is RGB. So you have the red channel, green channel, blue channel, just like colors. In this case, you're actually taking a cube, and you're multiplying a cube times cubes of the image, and then you're moving cube by cube. So the filter now, so now we have this, I can't see it here. How do I get rid of this, Shakir? You always know these things. Let me try to click here. Oh, wait. There, it's gone. So the filters, this, oh, it's because I'm close there. 3 by 3 by 3. Anyway, 27 parameters. But you can also apply filters that, like one filter that produces this image, and then apply another filter to produce this image. So you can go from a cube to a cube. And these cubes is what, in today's language, we call a tensor. So think of it as three-dimensional matrix. Hence TensorFlow, that operation. And TensorFlow allows you to do that operation efficiently, and it uses GPUs. The magic of distributed computing is what made a lot of deep learning possible. And you can use GPUs, you can use ASICs, all sorts of technology for doing this. This is something you can verify also in the comfort of, in the privacy of your room tonight. You can check that if your input is n by n and your kernel size is k by k, then the output size will be given by this number. This particular type of convolution, where you stay inside the image, typically gives you an output image that is smaller than the original image. It's called a valid convolution. TensorFlow offers several of these different types of convolution. Another trick that people do, if you want to preserve the size, so you want an image that sort of, as you convolve, as you go up and add more convolutional layers, you would like to still have an image of the same size. And this might be because, for example, you're doing some medical imaging where you take the input image and you want to predict an output image where you highlight in red where a tumor might be. So you still want to keep an image. Or if sometimes in games you also want to maintain an image. So this is called SAME, and I think it's what you use in your tutorial. Okay, the other thing you can do, you can also, we were moving pixel by pixel, the patch, but you can also do jumps. So we call this stride. So you can move 2 by 2. You can take gaps like it's happening here. So here is jumping. So it only does it 3 times. And that might give you sort of a bit further speed. It can give you some local invariance, which I'll explain a bit better when I talk about pooling later. An alternative you can do is you can do dilations. This is actually a very cool operation. And it turns out to have played a big role in recent developments in deep learning. So a dilation basically now allows you to, whereas with this patch, I have to just look at the local region. So if I want to find Shakir, it would take me a long time because I'm going to go person by person, person by person. But if I had something that sort of could do a bigger, like filters that could do scans at different resolution of the image, then there would be something overall. There's something more or less looks like Shakir, and then I could zoom in and get Shakir. And so for applications like, so recently, for example, there's this paper called WaveNet that was going from text to speech. And it's the sort of thing that you will be using when you get, when someone gives you instructions, when you talk to someone on the phone or whatever, and they give you instructions in some natural language, mapping text to voice. We'll be using that technology. It's also used for sort of image processing. So there's also things called pixel CNNs that allow you to generate images that use this operation. So dilation, super useful. And you can also do the opposite. So you can also, either through doing zero padding of the image or by increasing the filter, you can also upsample. You can also select your weights so that you increase in resolution. So that's also a perfectly fine thing to do and easy to do in TensorFlow. So basically, to summarize, suppose you have an image as input that's 3 by 3. So this is the image. And in this slide, I'm going down as opposed to up. So you can compute a single neuron by multiplying the filter that in this case is 4 by 4 by 3 to produce a single output. And then you produce another output just by moving that filter. And by moving the filter all over, this filter W1, you get an image. Then you take another filter. So that filter could be, for example, a Shakir detector. And then I could create another detector, a laptop detector that detects that laptop, and so on. So each of these filters will be tuned. Will be one of those many little images that we had before that's searching for the different patterns in the world. And so that's pretty much how we build this. So typically your tensor will specify how many, we call these things channels. So that's 2 channels here, 3 channels here. You need to specify how many input channels you have, how many output channels, and what's the filter size. In this case, height and width, 4 by 4. And of course, you need to specify strides and all of these things that we did before. Another operation that used to be popular, perhaps less now, is this operation called pooling. What pooling does is it looks at the region of the image, and it might just pick, say, the maximum value in that image or the average value. And it's a way of condensing the information of a small region into a single point. If you pick the maximum value, then it doesn't matter if, like, Shakir is slightly, if he moves a little bit, it doesn't matter, that sort of local perturbation will not affect my classifier because I'm already assuming that I'm searching for something that is in a small region, that the max could be moving a little bit. And that's a kind of also invariance that I alluded to before. Okay, so one of the, so basically now to sort of put a bit more, for those of you who are more math inclined, what you essentially are doing is in going from this input tensor to this output tensor is we're multiplying it times this weight that has some width and some height, this filter. There will be, say, F filters. In the beginning, there's F channels, and then there's F prime channels. And you go from X to Z, I prime in the output, I and J without prime in the input. And I'm going to use this to derive a mathematical expression for this operation. I've already done it with a 2x2, but I'm going to try to generalize it so that this ties with your exercise. One way to think of a neural network, and this is one of the most important slides in neural networks, because this is the thing where, where the Lego happens, is you can think of a neural network as having many layers, where you take an input, you process this input by a layer, and then by another layer, and so on. And eventually there's a last layer that tells you how good your performance is, the cross entropy, and that's the value of the cross entropy. But then what you do in backpropagation is you look at the errors, you check how many errors you start, and then you also send back a derivative message. You start looking at the derivative of the energy with respect to itself, then the derivative of the energy with respect to this output, and so on. Because essentially backpropagation is just a chain rule. It's just a way of computing the derivative, the gradient, to find which region should you go down. And so to compute the derivative, if you know the derivative here, you can compute it here just by knowing what function is implemented by this module. So the beautiful thing of the whole of deep learning is that modularity. That if you're assembling a big system like this, you only need to make sure that the single piece works. If this piece has an input to output mapping that matches and a corresponding derivative backward message, so this being the derivative with respect to the output, this is the derivative with respect to the input, and you also need, of course, the derivative with respect to the parameters. But provided you have this, what we call the forward message, and the two backward messages, you're done. That's how you specify a piece of code. And if you go, for example, in Torch, this is more clear. So if you go to PyTorch and you look at a module like a linear layer, for example, or a sigmoid layer, each of these units of software is implemented like this. You basically have a file, and in this file, you will specify what the forward message is, you specify what the derivative is, and so on. And if you create this an interface for this file, for this module, now everyone can use it. And you can just plug it anywhere, and it will automatically work, because it's constructed in a way that you respect the chain rule. And then once you've put many of them together, this itself, the whole thing, is also a module. So you can actually put that module on the web for other people to use. So yeah, never forget the Lego image. So again, in general, we have this forward message. So we have an input Z, a layer at layer L, which has may or may not have parameters, and it produces an output. This is some arbitrary transformation that's differentiable. And then the delta message is basically the derivative of the error with respect to the variable Z at layer L. And you can compute it by using the chain rule. So if you know the one before, the new one, you just need to know which transformation your module implements. So your input goes from ZL to ZL plus 1. And if you know that local derivative, this one came from before. It's the message that was sent from upstairs. So you only need to know your own thing. So even though you're doing global computation, you only need to know the local. Of course, to do this, you first need to do a forward path, and then you do a backward path. And even this is changing. People are figuring out ways of doing this so that you don't have to do the forward and backward. Okay. Some more math is how you would do this. Matrix operation, if you decompose, make the matrix operations in sigma notation. And of course, you do this for the parameters. And once again, the parameters, you only need the backward message. You only need to know your local thing. So if you know the local information of your module, everything works out nicely. For a linear layer, the transformation that you do is this dot product, input times parameters. And so you can actually show that using the rule for the backward message, you can get the two derivatives. The derivative with respect to the input and with respect to the parameters. And that's the specification. So in the code, you only specify this and you're done. That's a linear layer. And anyone else can use it just with one line of code from now on. And so folks have done this for everything. There's ReLO layers. The conv layer, it's this correlation. If you do it for images, now you have height by width this is the filter theta. You have height by width. You have the number of input channels. You have the number of output channels. And this is the input image. And you just multiply it for every possible coordinate, and that gives you the output. And then as an exercise, you can go and play with a bit this and check the derivative would be this. And again, if you have the message that's coming from above, you only need to worry about this derivative, which actually I've done. It's just the derivative of this with respect to theta is just dx. And then you can also compute the updates for the backward messages. With the pooling layer, you take the max of a region, and it's also trivial to compute the derivative. So I'm not going to go all this math. It's a bit tedious. It's best if you do it on your own. But this is where knowing derivatives is useful. If you want to build your own module, and you come up with a new function, and you want to represent, you want to sort of wrap this module and put it out there for PyTorch or in Sonnet for TensorFlow. Is Sonnet public? Okay. There is this thing for TensorFlow called Sonnet that has exactly the stuff of structures. It tries to implement this. And tf.nn, the neural network thing, it's that we've been using, that I was using in the code, is using the same idea. This is how these different things are put together. Once we have a layer, we can go all convolutional, and we can build large convolutional networks. So for example, here, we're building one convolutional network that has, it starts with the image mnist, and then it will do these different operations. So first it uses 4 channels and a stride of 1, then 8 channels and a stride of 2, and so on. And in TensorFlow, you would just basically, this is the first, you allocate the variables and specify the variables in the graph, which are the weights and the biases. And the way you specify a filter is the size of the filter, size by size, the width, the number of input channels, the number of output channels. Just like the math, the code is the same thing. When we apply a transformation, like a ReLO, and this is the convolution function, by the way. And see, this is TensorFlow.nn. nn.conv2d, that's one of those modules that someone built for you. They figure out the derivative, they figure out what the forward operation is, and so if you look inside that piece of code, you'll see the forward and backward operations. I guess for TensorFlow, for Torch, you can easily look inside the code. For TensorFlow, it might be a bit more work. For Sonnet, you could still look into it. So some of these functions are highly, for efficiency when implementing TensorFlow and so on, they might sort of go to some low-level language or so to make it. So it starts becomes obscure how this gets implemented. In fact, that's the beauty of it. So there might be different obscure implementations of this that involve compilation and so on, so that it can run on your phone as well as your desktop. And that's basically, you specify the strides. This is the type of convolution here. This is what I mentioned. You specify whether it's valid or same, and I think there's a few other options. You might have to reshape the data so that you can do valid multiplies. But that's pretty much it. That's the whole network. And usually when you implement this, you would create, like in the tutorial, to make the code cleaner, you would create a class where you basically specify the model, and then you create another class or another function that trains the model, and then some other function to just visualize the results and look at the accuracy and so on. But that's pretty much it. That's a ConvNet in TensorFlow, those 6 lines of code. And when you try this, you also see that it doesn't work so well. It actually doesn't get very good accuracy and so on. And so what he did here in his slides was when things don't work in deep learning with ConvNets, often people just, the way they deal with it is they just make the model bigger. That's one way to do this, especially at Google where you have the computing that allows you to do it. So you make your model bigger. And often the models do have to be big, because if you're doing something like general, I think for MNIST an overkill, but if you're doing real images, if you want to detect pedestrians, I mean, the visual system is big. That's a third of your brain. It's a lot of computing going on into it. So we do need big models, massive models. They're still short from the trillions of parameters. So another thing he did here is he did the dropout in the model, made it bigger, but also did dropout. And when he did that, the results improved. So the test loss went down, training, so you might be able to attain a smaller error. So sometimes dropout does work. Of course, the other thing that folks have been doing is they've tried to go bigger. And so start with an image and go to much bigger networks that involve multiple convolutions and max pooling operations and so on. And this is pretty much what Karen Simonian, who did the slides, was doing before. Actually, I forgot, let me skip these. And so he was involved in this competition, ImageNet. So around 2000 and like mid-2000s, there was a group in Canada that was doing a lot of work on deep learning. And this is like Yoshi Bencher, Jeff, and it was sponsored by the Canadian Institute for Advanced Research. Andrew used to attend, I used to attend. Shakir was a fellow, one of the junior fellows of the program. And we had, we believed that this was the future. I remember presenting a convolutional neural network for video. And of course, this thing took my student about a month to train. And it was simple videos for activity recognition. But we really felt this was the way forward, that these models could do lots of things. They're very flexible. You can get them to do anything in terms of the data changes. They're modular. You can build all sorts of modules. But we didn't have the killer results. And so Jitendra Malik then proposed that ImageNet should be one of the data sets we should try. It was this huge big data set that had been created in Stanford. The details are here on the slide. And so if we could train here and do well, and this was a competition where the computer vision people have been going at it, then they would pay attention to us. The vision people would pay attention to ConvNets. Nowadays, if you go to a ConvNet workshop at any vision conference, there'll be like 3,000 people listening to whatever you have to say about ConvNets. In those days, no one thought they were relevant. And so Jeff Hinton took the challenge. And he had the vision that the way forward to go is to do distributed computing with GPUs. And so I even had a workshop in Toronto about this and so on. And then it wasn't long before it was finally cracked. And the year was 2010. And actually, this slide doesn't show it. But before 2010, the handcrafted solutions were getting errors of 40-something. So when the deep network came, trained on a GPU, the drop was vast. That day that those results were reported, I think the field of computer vision changed forever. And then there was some improvements. There was this network that I showed you before with all those filters corresponds to this result that came the next year. And now the authors, actually, one is at Facebook, Rob Fergus, and then the other one is the CEO of Clarify, a successful company in New York. In 2012, that's when, trying to get my dates here, time goes by. I think that's eventually when VGG, oh wait, I'm getting this wrong. When did, oh, the dates are here. I'm getting it all wrong. Sorry, this was the error, because this is in classification. Okay, this is the classification, this is what the vision people were doing. And then AlexNet, when Alex Krzyzewski was the student working with Jeff Hinton, he comes and implements it, and they were tuning by little bits. This was like speech recognition, where every year you tune, you get a little percentage of gain, and this was significant. But then this model is just like, boom, creates this big drop. And then comes Matt Zeeler of Clarify, and then VGG of Karen, and then so on. Then becomes the realm of the ResNets that we will get to. Okay, so AlexNet was like this. So it was a simple convolutional network, like I've shown you before, with some pooling operations, and then some dense layers, and then the output. So this is sort of a canonical neural network now. It basically puts together all these elements that we've discussed so far. So you can implement this in TensorFlow, just a little bit of code, and be done. It ran on a GPU to be efficient, and I think he did 2 channels to get some extra performance on the GPU. And this was a particular structure. So one thing that folks realized, and especially as they went in further years, like Matt Zila and Karen, was that by adding more layers, the results got better. Okay, so this was, before it was a hypothesis, but they actually proved it in the competition. Which is another sort of important thing. You can have great models and great ideas, but unless you get, you run experiments and you follow the scientific method and you actually validate your theories, check whether things are working, it's going to be hard for you to convince other people. The best way to convince other people is by actually getting good performance on data sets. So they found that going deeper is better, even though there's some issues with, sometimes issues with training, and of course, the deeper you go, the more operations you have to do. But a nice thing about going deeper as opposed to wider is that you're composing. You have a function of a function of a function, so you can get more complex functions by going deeper. There was also biological desire to do this, because we know we have these multiple layers of processing, so we wanted to do something like that. And so, in between the pooling layers, what folks started doing was doing this sort of stacking, putting many convolutional layers. And I'm not going to go into details, but through doing stacking, they were able to go and improve results later in 2014 and so on. And note how the number of layers was going down, 19 layers, then 22 layers. But stacking wasn't enough. And then later came something called a ResNet, which I'll get to. And a ResNet allowed us to go to very deep models, 152. Now, before we get there, so Karen, to give you an idea of where we were before ResNets, the best that we had were the VGG nets, which are still awesome nets. So the VGG nets, they sort of involve many steps of convolution. So they do this stacks of convolutions followed by pooling. This is highly engineered. What Karen does is he sits down and he tries one thing, and then he tries like another thing, and then he thinks about it, and he keeps sort of thinking about these different versions. He measures the errors of these different versions, and he runs multiple tries to figure out which one is best. So this is still so a big part of this still is experimentation. But eventually, Karen hit a limit. He couldn't go, I think, gets to this size of 19 layers, and then things are not working. Going deeper is not giving him better results. And the problems that he encountered were the following two. One, that as you go deeper, you're applying more operations, your matrix vector multiplication, so things start becoming very expensive. And the other thing is, it's hard to train these networks as you go deep. As the gentleman pointed out earlier today, I'm not going to go into the mathematics of it, but I have a lecture on YouTube on recurrent networks that actually does the derivation of why this happens. But the deeper you go, the harder it becomes to propagate information. If you make your parameters be, sort of loosely speaking, if they're too small, then the signal vanishes. So it's like one person communicating to the next person, to the next person, to the next person. And so if the signal is being attenuated, eventually the message doesn't get to the person at the top left there. If someone screams too loud, then it becomes really loud, hard to hear, then everyone starts screaming, and then that person, they will get a message, but it will be completely wrong. The thing just blows up. And so that's essentially what's happening with the signals propagating through the net. And so optimizing these networks is difficult. There's many algorithms out there that we use. Usually the ones that work better are things like SGD, RMS prop, Atom, or Momentum. But the training, if the networks are large, is unstable. Either because if the weights are too small, the gradients finish. If the weights are too big, the gradients explode. Both being undesirable. So here's one solution that helps with the training, and it's batch normalization. And this is not the only way. There's also initialization and so on. They help to some extent. So as this plot from the paper of batch normalization shows, this is the sort of the accuracy on MNIST. This is, the dashed line is without batch norm, and this is with batch norm. So it works much better. What does it do? What it does is it standardizes the input data and the activations in each layer. So the idea is, so what tends to happen is that some of these, especially with the parameters changing, sometimes a small perturbation of the parameters makes the activations, the responses, the images further up, change a lot. So the networks become unstable. And so what the batch norm operation is, it computes for the whole map, for the whole image, you compute the mean over a mini batch, or you might even do it over the image. There's different ways of doing this. One is called the normalization. If you have a covenant, typically you normalize by taking the average over the whole image. Or in this case, the standard batch normalizations, you take a batch, you normalize by taking all your data in a small batch. So you compute the mean, and you compute the variance, and then for your image, for each image, that is each activation map, you subtract the mean and you divide by the square root of the variance, by standard deviation. So basically, this is basically the equations to implement it. You compute the average of, say, in this case, the input image. You compute the variance, and then you subtract the average, and so on. And then you create a transformation, which is the batch norm layer module, and you package this whole thing as a layer as well, and you can write the expression for its gradient, so you can differentiate it through it, and you create a module. And again, in TensorFlow, this is one line of code, because someone already did that for us. And essentially what this is doing is making sure that each of the signals, each of the images has values between, is sort of normalized to be Gaussian 0, 1. And so they will all have the same magnitude, so they're not going to be oscillating wildly. And this helps. So when you do this, as you increase the number, so previously the errors tended to be for VGG models. What Karin found that was unacceptable was that the deeper the model, the higher the error. But once you applied batch norm, actually I don't have it here. Once you applied batch norm, he was able to get some better performance. I'm missing the one slide where that explains this. Oh yeah, sorry. This I think was with batch norm. This is before batch norm. But even that is not a big gain. The real sort of big transformation, I think this was one of the coolest ideas of the decade, was residual connections. It's a very simple idea. So the idea is when you have some layers, you add these skip connections. So basically, this implements a transformation, f of x, so the input is x, multiplying by a weight layer and a ReLU function and another weight layer gives you a transformation f of x. And then you add x to it to produce the output. Now, why is this a smart idea? It's smart because when the gradient comes back, it can either go through here, but it also can go through here. So you always, so there's not, if the weights are small, it's not going to vanish because it has this other channel to go back. So your derivatives are much better behaved. So this simple idea was all that was needed to be able to go deeper. And indeed, I went deeper. Another way to think about this is that every time you get these different routes, depending which route you take, you can actually sort of expand this. And what you have is actually a combinatorial combination of networks. You can sort of expand the mathematics of this. And what you have is a network with a huge capacity. And by doing these skip connections, we could go much deeper, and we could get to beat humans on this particular data set. One of the problems with these networks, however, and with all the convolutional networks, is something called adversarial examples. It is possible to construct an input image, so by adding noise to it, that will make the network think that that image is something else. So you can take an image of a stop sign, and you add some noise that to the human eye is imperceptible, and then the network stops predicting that it's a stop sign. That's called an adversarial attack. That is becoming very important, and it's important for two reasons. For actually many reasons. One is because it tells us that even though these models can outperform humans on image classification, that doesn't mean that they're the right models. Because we humans look at this image of a stop sign, which has been corrupted by noise, and we still see the stop sign. So it makes us think that we need to think about how to, our job as cognitive modelers is not finished. More research is needed. It is also important because of the adversarial could be an actual adversarial in the world. So imagine you built cars to detect pedestrian. Someone hacks into it by adding noise, and all of a sudden, you can't tell what's going on. There's this noise that comes into some component of the camera that makes the car no longer see pedestrians. So you need to create the right security to protect your systems, or we need to design better networks that are not susceptible to this problem. One of the key problems here is that these are correlation models. They learn to predict. This input matches with this output. You're learning a correlation. These are models of prediction, of correlation. These are not models of causation, and that's part of the problem. There is no top-down. Like in the brain, you have all these top-down connections, and you might sort of predict that it's a stop sign, and then you double-check, or you have this wider context of information that you use to sort of confirm a hypothesis. That confirmation process is not in these models. So you're not actually trying to check whether the predictions. Humans can also be fooled, by the way. So we often misjudge causal statements and so on. The other thing about this is, here this is important to keep in mind, these are models of prediction. And right now, people are using them sometimes as models of causation. And this can cause all sorts of biases. Because they might take, like I've seen some of these examples where they might take a batch of images. They take a bunch of images of people in jails in California, a bunch of people of images of, I don't know, hipsters in Oregon, and then they try to build a classifier to predict criminal versus hipster. And the fact is, yeah, given the data set that they collect and so on, it works. But what doesn't mean that it works? It's learned a correlation. But you cannot now use this as a model to go and predict whether someone is a criminal. Because all you're doing is you're reinforcing the bias that exists in society. What makes you a criminal is the act of committing a crime, not your appearance. What makes you gay is whatever acts you do for fun in your bedroom, not your appearance. And just now there's a paper that's also popular trending on the web about this. And this happens over and over again. It's important to think that causation is about acting, about interventions, and so on. It's not about correlation. if you get a chance, there is one technique that is very important. And it's no longer taught in machine learning. It's taught in econometrics, and it's taught in biostatistics. And you can just go to the Wikipedia page for instrumental variables, or you can go to the Wikipedia page for causality. Make it part of your education to know very well these topics. Because otherwise you're going to... One of the big things we need to fight now in the world is ignorance. And there's no worse form of ignorance than someone who can use TensorFlow and code a ConvNet and apply it to data, but knows nothing about causality. Because that person becomes dangerous for society. Especially if there's a lot of people who don't know that person doesn't know and start following that person. And these days that happens a lot. So always be careful with what the models are saying to you. So once you use a ResNet, you do get the property that as you go, so whereas before, with a simple model without residual connections, the higher the number of layers, the worse the error. Once you add the residual connections, by going to more layers, the error goes down. So this pattern gets inverted. So residual connections, very important. ResNet's one of the best models you can use out there right now. That's what you want to use. Now, very quickly now at the end of the lecture, I'm just going to go over some other applications of ConvNets. Like I said, you can apply this to all sorts of data. Sometimes we don't just do image classification, but you might want to process an image. So folks might be interested in segmenting an image. You can actually go the other way around. I don't have, I can find a video for you later. But you can also go from segmentations to images. So someone gives you, like, there was this very cool paper recently where they take Grand Theft Auto, the game, and then they go from that to generate the actual real images and so on of the city, from segmentation mask to it. And these type of models, there's one in particular called a UNet and so on that sort of goes down and then up. And just basically all convolutions with residual connections always. And then you can do all sorts of image processing, so especially for medical processing and so on, that can be very useful. You can also apply ConvNets to video, to like Karen did in this example with Andrew Zisserman to extract optical flow, to extract motion. This is another example of that some of my students, Brendan Schillingford and Yanis Assel, did for doing lip reading. So going from a video of just your lips moving to being able to say what you're saying. And for a lot of data sets, they get superhuman performance and by human experts. And this is important, not just from a perspective of creating interfaces, but in the UK alone, about 100,000 people have tracheotomies. I think I found that figure in YouTube, on the web. And a lot of these patients, because they have a tube implanted here, because they might not be able to create sound loud enough. They can move their lips. And so with this, we will be able to provide devices for people to be able to communicate with their loved ones or with doctors and nurses. Sometimes, and here is what the brilliancy comes in apps. So a bunch of researchers in Stanford, they actually took a convolutional network, a VGG network, I think. And then what they did is they just took a bunch of satellite images. Using the trained network, they used it to extract features. And then they just, from those features, they started, for some parts where they actually had indices of the wealth of that in that region, or the poverty index for that for a particular region in the world, and they were using images during the day, night images and so on. They learned actually to go over the entire Earth and extract, actually not the entire Earth, they did it for several countries in Africa, extract the poverty index for different regions. So it's an alternative to doing a census. Instead of doing a census, which might be prohibitive in some places, with this we do it automatically. Who knows what statistics means? Where the word comes from? Statistics is related to stata, or the state. And that's when folks in Germany and Sweden, there's a few different tales, I'm going to skip them, wanted to know what's going in the nation. Like imagine you travel back a few hundred years, you sort of have horses and carriages. It's very hard for you to know what's going on everywhere. You're the king, you want to figure out like, okay, are people evading my taxes? Is my army bigger than my neighbor's army? That sort of thing that kings, I guess, worry about. And so they decided to do countings, to go out there and figure out what is the state of the nation. What's the stata? And hence, statistics was born. Statistics is about knowing what's going on in your city. Knowledge is power. Knowing what's going on Earth is important. If you work in data science, for example, at UNESCO, you'll find that you need to know where the children are. Where are the children that need water? I mentioned 1.2 million people dying of car accidents. 3 million die because of diarrhea. Where are those children? Because a simple app that's delivering water could help them. And speaking of delivering water, this is another crime. Plastic. We've used it for less than 100 years, and it's creating serious environmental. So one thing is how do we get rid of the habit, and then the other thing is how do we use the same type of techniques, being able to get the state of the world to know exactly how big is the problem, how much plastic is deployed out there. How can we sort of figure out, how can we engineer data sets in a smart way? The guys at Stanford, they like realized, we could use these night images from Google because there's the light intensity that tells us more or less how populated an image is and so on. So figuring out which data set to use as an input and then what as an output is a big part of the game. ConvNets also can be used for all sorts of, and I think I'm out of video, but they're also the things that we use like at DeepMind, like to play Atari games. So it's sort of, the ConvNet looks at the screen and then it chooses joystick actions as the output. And you'll learn through RL, which you will learn after tomorrow, you'll learn how to choose a policy. And a policy is a network that takes as input the image, and as output it tells you what to do, what actions to select. So these networks become very good at playing games, different types of games. And how many of you heard about AlphaGo? Okay, well, eventually those networks became, so for those of you who don't know, Go is sort of a big game. It's played, it's one of the most popular games in the world. We live in a small part of the world. Asia is big in terms of people and so on. Where the game is mostly played, that's what it looks like. So it's an image. And you can apply a ConvNet to that image. And in particular, what you can do is you take a ConvNet. So first you can take if you want, you can take human data, and you can, from the human data, basically, given the board position, what someone did in the past, and you can learn a ConvNet classifier that will predict which action to take, which sort of piece, which stone to put. But what you can do that's even more interesting is you can do self-play. The idea is you have a ConvNet play against another ConvNet, and the ConvNet that wins sort of becomes the new champion and reproduces, and then those two ConvNets start playing against each other, and so on, until you get a better ConvNet. And you also can get a value network, which basically says how valuable is a particular position in the game. What are your chances that, how much would your value increase the chances of you winning the expected reward by putting a stone in, say, on the left, versus on the right. So there, for AlphaGo, the key models, so there's 3 components. There's still a search tree for planning, but the key models are a neural network that looks at the game through a convolutional network and predicts which actions to take, where to place a stone. And then there is a network that looks at the board and tells you how valuable is this current position. What is the expected chance that I will win this game, given the way the board is? And that's very useful, because when you do planning, you basically do rollouts into the future, and you can use this network to estimate, if I were to do this and this, will I be in a better position? Or if I were to do this other thing, will I? So you sort of imagine and run all these counterfactuals in your head to figure out what's a better position. Anyway, the thing that's relevant for this course, for this lecture, is that these were all convnets. So knowing convnets, as you can see, can take you a long way. Deep learning is like Lego. You learn a few basic pieces, the linear layer, the ReLU layer, the batch norm layer, the residual connection trick. You learn the conv layer, maybe the pooling layer. These are all different types of Lego pieces. But to build the systems, we just put them together. And some folks have put them together in very interesting ways, like the ResNets and BGG networks. And so we just reuse those networks. Don't even try to come up with something more exotic, because they've already been tried and proven. And that, I would say, is the strategy for going ahead. The challenge is to figure out what data sets to come up with. Oh, this is the sort of history of Go, but I'll stop here.